Hi, my name is Harlan. Welcome to the H Matricon Mechanical Engineering channel. Last week, we have discussed about the basics of heat transfer fluid systems in an industrial application. And now we would like to uh, present an analysis of an existing heat transfer fluid system in a manufacturing facility, and it is a primary secondary uh, pumping circuit. And since this is quite a lengthy a discussion, so we have divided it into two parts. The first part will focus on the primary pumping circuit, and the second part will be the secondary pumping circuit, wherein you have the four users. So today we will talk about part one, which is the primary pumping circuit. So in the primary pumping circuit, we have an oil heater, which is gas fired, and the capacity is 10 million BTU per hour with an economizer. And the oil heater is situated in a separate building about 100 feet away from the users. And the circulating pump is rated at 400 US gallons per minute and a head of 125 feet. But the actual flow is only 260 US gallons per minute as measured by the ultrasonic flow meter. And the spare pump, we have a spare circulating pump, which is connected in parallel to the main circulating pump. And we have a filter, which is connected offline. So it shows here the P and ID diagram. We have the gas-fired heater having a capacity of 10 million BTU per hour output, and with 2.5 coils. And we have a relief valve here and orifice plate flow meter, and it goes to the supply line leading to the users. And from the users, it goes back to the return line to the deaerator and back to the uh, circulating pump. Okay, and so uh, what is the problem? The problem is the discharge of the circulating pump is only 260 US gallons per minute compared to its rated flow of 400 US gallons per minute. So how are we going to approach the problem? We calculate the system head and compare it with the rated head of the circulating pump. Let's go now to the computation of the required pump head for the primary circuit. Total head is equal to the pressure head, P over gamma, plus the velocity head, V squared over 2 times acceleration due to gravity, plus the elevation head, Z, plus the head loss. And take note that this one here, the second item in the total head, which is the velocity head, this can be excluded because the value of this expression here is very small that it can be neglected. So the total head E over gamma plus Z plus H sub L will be the total head. So let's start with pressure head. The pressure head, will solve for the pressure head for a given operating pressure of 15 psig and a density of CalFlow AF heat transfer oil at a temperature of 260 Celsius. The density is 44.7 pounds per cubic foot. And pressure of a gamma, which is the pressure head, will be equal to 15 pounds per square inch times 144 inch squared per foot squared all over 44.7 pounds per cubic foot. The result will be 48.32 feet. That will be your pressure head. The velocity head, I said it is negligible, and I just like to show to you at this point in time that it is really negligible. So solving for the fluid velocity at 6-inch pipe from the continuity equation at 400 US gallons per minute discharge, we convert it to cubic feet and we per second, and then all over the area. So you will have the velocity. So the velocity here, because we know that from the piping systems manual, for a 6-inch carbon steel pipe, the diameter is 0.505 feet, the inside diameter. So plugging in all the constants, we have velocity is 4.45 feet per second. The next step, then we put in this 4.45 feet per second to your equation and divided by 2 here, and the acceleration due to gravity is 32.2. The result will be 0.307 feet, which is very small, so negligible. So in the succeeding calculations, we will omit the expression v squared over 2g. For the elevation head, the highest point in the pipeline, the elevation will be 20 feet. Now let us go to the head losses. The primary circuit consists of the oil heater, the orifice flow meter, the pipeline components that are basically in 3 different sizes, 2.5, 4-inch, and 6-inch. Let us consider first the head loss in the 2.5-inch pipes and fittings. So from the piping systems manual, the design value of the absolute roughness for a steel pipe is 0.0002 feet. And the relative roughness is equal to the absolute roughness divided by the diameter. So the diameter of 2.5-inch steel pipe is 0.206. So divide 0.0002 feet by 0.206 feet, the result will be 0.00097. It has no units because it is a ratio. And the kinematic viscosity of our heat transfer fluid, which is CalFlow AF, is given at VIS sub K is equal to 0.7 centistokes. And convert the centistokes to stokes here and convert it from stokes to square meters per second and convert it to square foot per square meter, a square foot per second rather. So you will have 7.53088 times 10 to the negative 6 square foot per second. And from the kinematic viscosity, we can solve for the dynamic viscosity by multiplying the kinematic viscosity by the density. So we simply multiply 7.53088 times 10 to the negative 6 square feet per second times 44.7 pounds per cubic feet, and the result will be 0.0003366 pounds per foot second. And solving for the velocity of the fluid inside the 2.5-inch steel pipes at 400 US gallons per minute. So you will have, if you convert this to cubic foot per minute and then cubic foot per second. So The result will be square feet, feet per second. You have the area pi point times 0.206 quantity squared divided by 4. The result will be 26.74 feet per second. So the next step is we calculate the Reynolds number. Density, 44.7 pounds per cubic foot. Velocity, 26.74 feet per second. And the diameter, 0.206 feet. And the dynamic viscosity is 0.0003366 pounds mass foot second. So the result will be 731,513. And from the Moody diagram, using the values of absolute roughness, this one, of 0.00097, and the Reynolds number of 731,513, we locate the Moody friction factor F is equal to 0.021. Such flow pattern is approaching complete turbulence. We'll show to you how it was being located. So this one here, the blue curve is the relative pipe roughness, and this one here, the vertical lines, grid lines, are the Reynolds number. So once you have located the Reynolds number, you have located the curve here. For the absolute roughness, you can read the friction factor, Moody friction factor, 0 to 1. And referring to the piping systems manual and tabulating the friction components, we determine the total length, equivalent length of the setup. So these are the components of the 2.5-inch piping system, the quantity of each component, and the unit length. This comes from the piping systems manual. You multiply, you get this equivalent length here, and then get the total to get the equivalent length of the run of pipe. And solving the head loss for the specific run of pipes here, 2.5. This is the Darcy-Weisbach equation. The head loss H is equal to the F, which is the Moody friction factor, and L sub E equivalent length times V squared, which is the velocity in feet per second, all over 2 times the inside diameter, which is 0.206, and G 32.2 feet per second squared. The result will be 128.8 feet for the head loss. Let us consider now the head loss for the 4-inch pipes and fittings. So we compute the relative roughness of the 4-inch tiered pipes, 0.0002 feet, divided by 0.336. This one is the inside diameter of a 4-inch steel pipe. The result will be 0.000595. The dynamic viscosity of CalFlow AF heat transfer fluid has already been determined in our previous calculation to be 0.0003366. So the next step is solve for the fluid velocity along the 4-inch steel pipe at 400 US gallons per minute discharge, and convert it into cubic feet per second, and divided by the area, which is pi d squared over 4, wherein d is the inside diameter of 0.336 feet, and the resulting velocity will be 10.05 feet per second. Then we calculate the Reynolds number. We have the Density 44.7 pounds per cubic foot. We have the velocity 10.05 feet per second, and D inside diameter 0.336 feet, and the dynamic viscosity 0.000336, and the result will be 448,434. And from the Moody diagram, we using the values of the relative roughness of 0.000595, and then the Reynolds number of 448,434, we locate the friction factor 0.018, and it falls right at the boundary between the transition zone and the zone of complete turbulence, shows here. So this is the relative roughness, the blue line or the blue curve here, and this one here is the Reynolds number, the vertical lines. So you locate it here, and we read out the value 0.018 Moody friction factor in here. And so take note that the red curve here is the complete turbulence. So it is in between, just in the boundary between the transition line and the complete turbulence curve. So from the manual and tabulating all the friction components, we determine the equivalent length of the setup for 4 inches. So these are the components, quantities, and then equivalent length from the piping systems manual, and we get the total equivalent length here for each component, and the overall total is 53.7 feet. And we go now to the calculation of the head loss for the run of pipe, which has the size of 4 inches, and we refer to the Darcy-Weisbach equation. Head loss is equal to the Moody friction factor, L sub E, which is equivalent length, and V squared is the velocity squared, all over 2 times inside diameter of 4-inch pipe, and acceleration due to gravity. So friction factor 0.018, L sub E will be the total equivalent length is 53.7 feet, and V is equal to 10.05 feet per second. The diameter is 0.336 feet for a 4-inch pipe, and the acceleration due to gravity is 32.2 feet per second squared. And we can shorten our calculations, although what I am doing right now is solving it the way it should be. But a shorter way of doing it, anyway, it has only very minimal error, is this value 0.018, as you have determined from the Moody diagram. We have already determined for the 2.5-inch pipe that our friction factor, the Moody friction factor, is 0.021. And we can round off all these values to 0.02 without much error. So what I do in actual practice, I just use, once I get the first Moody friction factor 0.021, I just round up all these friction factors for the different sizes to 0.02, for instance, and you will save time. But anyway, the head loss for this run of pipe will be 4.51. Then we consider the head loss in the 6-inch pipes and fitting. So again, we compute the relative roughness of the 6-inch steel pipe. We have the absolute roughness of 0.0002 feet, divided by the inside diameter of a 6-inch pipe, which is 0.505 feet, and the result of the relative roughness will be 0.000396. The dynamic viscosity of CalFlow AF heat transfer fluid has been determined in our previous calculations to be 0.000336 pounds per foot second. Then we solve for the velocity along the 6-inch pipe at a discharge of 400 US gallons per minute here. We convert it into cubic feet per second and divided by the area of the inside of a 6-inch pipe by quantity 0.505 squared all over 4, and the result will be 4.45 feet per second. Then we calculate the Reynolds number from the piping systems manual. We have Reynolds number, density times velocity times diameter all over the dynamic viscosity. So we have 44.7 pounds per cubic foot density, velocity 4.45, inside diameter of a 4-inch pipe is 0.505 feet, and this one is the dynamic viscosity 0.0003366. The resulting Reynolds number will be 298,432. And from the Moody diagram, using the values of the relative roughness and the Reynolds number, the result will be 0.017. So again, we can round this up to 0.02, as what I've said earlier. So here, from this pipe relative roughness here, and the Reynolds number, we can read out 0.017 here. So tabulating all the friction components of a 6-inch run of pipe and determining the total equivalent length, we have this. These are the components and the quantity, the equivalent length, unit equivalent length taken from the piping systems manual, and we have here the equivalent length, and then we get the total. So we have for the 6-inch pipes, using the Darcy-Weisbach equation, we can calculate the head loss. We have the friction factor F, 0.017, equivalent length of 954.5 feet, the velocity, 4.45 feet per second squared, and 2 times the diameter, inside diameter, 0.505 feet, and the acceleration due to gravity, 32.2 feet per second squared, and the resulting head will be 9.88 feet. The manufacturer of the orifice plate flow meter claims that at maximum flow, which is 400 gallons per minute, the pressure drop is 40 inches of water. 40 inches of water is equivalent to a pressure drop of 1.44 pounds per square inch, and therefore the head loss is 4.64 feet. Okay. The pressure drop on the oil heater was provided by the manufacturer at 90 feet. So the total head requirement as tabulated results in 303.4 feet. So let us see our tabulation. Pressure head for 8.32 velocity head negligible, elevation head 20, and we add the losses. We have a 2.5-inch pipes and fittings, 125 feet, and 4-inch steel pipes and fittings, 4.51, 6-inch pipes and fittings, 9.88, orifice flow meter, 4.64, oil heater pressure drop is 90 feet. The total is 303.1 feet. Now, our computation shows that the total head requirement is 303.1 feet. The actual flow measurement using an ultrasonic flow meter shows a flow of only 260 gallons per minute. This makes sense because although the feed pump is rated at 400 US gallons per minute and a head of 135 feet, the flow will be definitely affected if it is subjected to a head requirement which is triple its rated capacity. And it is worthy to note that from the piping systems manual, we show a recommended flow velocity for a pipeline in the range of 3 feet per second to 6 feet per second. And only the 6-inch pipes and fittings comply with such range flow velocity. And although the 4-inch pipes are quite close, but only the 6-inch pipes and fittings comply with the flow velocity recommendation. Let us then examine our list and our tabulation of the head losses and uh, see which of these has the highest value. These are, number one, the 2.5-inch pipes and fittings with a head loss of 125.75. And of course, we have the oil heater with a pressure drop of 90 feet. See, we have here your 2.5-inch pipes and fittings having a head loss of 125.75 and the oil heater pressure drop of 90 feet. So we focus our improvements, our planned improvements on these. So let us see how much improvement can be achieved if these 2.5-inch pipes and components are replaced with 6-inch pipes. So let us do a tabulation. Like say, since this one here has the highest head loss, we try to replace this with 6-inch and see how much improvement we will achieve by doing such. This one here, the oil pressure drop, we can't do anything about this because we cannot just say, oh, we'll buy another heater. Or second place, on the second place, we cannot reduce the flow velocity of the fluid in the oil pressure because it is really designed to have a greater flow in such a small pipe so that you will have a turbulent flow which is needed for an effective heat transfer. So this one is out of the question. You cannot do anything about it. So we will solve the head, determine the head of this run of pipe by changing this 2.5-inch to 6-inch. See what will happen. The relative roughness of a 6-inch steel pipe was already computed at 0.000396, and the dynamic viscosity was also calculated in our previous step to be 0.00033366. And the velocity along the steel pipe was also computed at 4.45 feet per second. And similarly, we have already determined the Reynolds number to be 298,432 and the friction factor to be F is equal to 0.017 from the Moody diagram. And from the piping systems manual and tabulating the friction components of this revised portion of pipes, formerly from 2.5-inch diameter to now 6-inch diameter. See, we tabulated it, so it's now 6-inch elbow, 6-inch T, branch flow, 6-inch T through flow, and outside stem and yoke gate valve, and 6-inch check valve, 6-inch pipe, and tabulate it here. The resulting equivalent length will be 239.7 feet. And we solved the head loss at this revised portion of the pipes from formerly 2.5-inch to 6-inch using the Darcy-Weisbach equation. You have the Moody friction factor F.017, the total equivalent length of 239.7 feet, the velocity of 4.45 feet per second, and we have here the inside diameter of the pipe, 0.505 feet, and the acceleration due to gravity, 32.2. The result is now down significantly to 2.5 feet. My comment, take note of the head loss is proportional to the square of the velocity. So as you increase the pipe size by a small amount, what will happen is you have substantial improvement in your head because it is the square. So the velocity here plays a lot in improving your head loss. So we will tabulate both situations. The original setup versus the revised setup. Original setup, 2.5-inch pipe diameter to 6-inch diameter here. See the improvement of the head loss from 125.75 feet here head loss to now it is 2.5 feet. And of course, it affects your total requirement. So it is now 179.9 or roughly 180 feet. So solution. Our solution is to replace the 2.5-inch run pipes, the run of 2.5-inch pipes and fittings in the primary pumping circuit to 6-inch diameter when a few more reactors, maybe 2, will be added to the process if you have an industrial or a plant expansion. This will increase the flow and the primary supply to a value of approaching 400 US gallons per minute. And we also keep in mind that when we plan for the layout of a new installation, make it a point that the oil heater room is located as proximate as available, proximate, close as possible to the users. So you will have a shorter run of pipe and you will have a lesser head loss. And of course, keeping the number of bends in the pipelines at a very minimum. So I hope you understood what I really want to drive into your imagination regarding the an actual installation of a heat transfer fluid system in an industrial setting. This is an actual project, and I hope you will learn a lot from this. And my objective is to transfer my experience to you, my dear friends, and of course to share my knowledge to other people. And the next video tutorial we will have is part 2 of the analysis which of heat transfer fluid systems in a manufacturing facility, and part 2 will focus on the secondary pumping circuit, which are now uh, involving the users. And I would like to thank you for watching our video tutorials at H Machicon Mechanical Engineering channel, and I hope you can also invite your friends to watch our video tutorials and subscribe to our YouTube channel, H Machicon Mechanical Engineering channel. Thank you. Bye-bye now.